So, last time we looked at Mohr circle in our general case, which is still drawn over here, and then we also looked at Mohr circle which had only compressive stresses. Then we looked at Mohr circle which had only tensile stresses, and we also said that there exists a no shear stress orientation, okay, which we said is this one when you have the diameter or the circle cutting the x axis. Now, the other question we want to answer over here, does there exist a plane where no normal stresses exist? So, in general of course, there does not exist such plane, but let us look at a particular condition. What will be that particular condition? So, let us draw it like this. So, we have a Mohr circle. Remember what is the x axis? X axis is normal stresses, y axis is shear stresses tau. Now, if we take a particular element which is in a condition such that the normal principal stress is sigma naught, which is equal to sigma 1, and again we are looking at 2 dimension, and sigma 3 is equal to minus sigma naught, meaning one principal stress is equal in magnitude to the third principal stress, but their signs are different, meaning one is tensile, the other is compressive. Now, in that case what happens? This y axis is now bifurcating this circle. Okay. Now, if so first let me draw that small orientation. When I say this, what I have is like this. So, this is sigma 3 compressive, which is equal to minus sigma naught, and we have sigma 1 equal to plus sigma naught. This is in tensile condition. Now, if I rotate this, this line represents the orientation of that element. If I rotate that line or the orientation such that the orientation is now represented by this line, see this, the diameter still crosses through the x axis, the 0 0. Okay. So, now our new orientation is this, and here I had to rotate, I can say counterclockwise 90 degree or clockwise 90 degree, meaning I am rotating this element by half of that 45 degrees. So, since this is a square element, I can rotate it this way or that way, it does not matter, which is also reflected in the Mohr circle. So, now my element is represented like this. Now, in this particular condition what has happened is I have a clockwise shear stress. So, if I call this as sigma xy, this is positive, and clockwise is called as represented by positive. So, this is sigma xy, and the other one is anti-clockwise. So, this is my sigma yx. So, this is sigma yx, and guess what is the magnitude? Can we say from this? Yes, we can say this is equal to minus sigma naught, this is negative, and this is equal to plus sigma naught. Why? Because this is the diameter. So, 2 sigma naught is the diameter, and over here also the diameter will of course for the circle remains constant. So, this length is represented by 2 sigma naught, and therefore, this is half of that, which is plus sigma naught, and this is minus sigma naught. So, our shear stresses are we know the magnitude of these shear stresses, and we also know that there does not exist any principal stress or any normal stress in this particular element. So, this is a particular condition or a particular case, you must remember. Not every element in a material or in a component which is being deformed or under some stress will have this kind of case, but you may be able to find some elements where you have positive stress equal to negative stress at that particular point and no shear stress existing. Then you can rotate it by 45 degree, and the same amount of stress actually is the shear stress, and there is no normal stress acting on it at that particular point. Now, since we are talking about this Mohr circle, I would like you, if you are interested, because this is a very interesting way to understand stresses and a very simple way to understand stresses, you must visit this website. You can just search on your Google or some search engine DOIT POMS. This is a website by some of the academic institutes in UK. So, it is dissemination of IT for promotion of material science. So, you will get not only information about this and many other related material science, materials engineering related concepts, but they also provide it in a very you can say animated way. So, you will get lots of animation, you can rotate, you can change theta angle, you can change sigma values, you can change sigma xy values and see how the circle changes. And so, you get to get a feel about the numbers and the construction of these Mohr circle. So, I would strongly advise you to visit DOIT POMS, just search on it and you will get it is doitpoms.ac.uk if I remember right, and you will be able to get not only information from about this, like I said, you can also get many other information related to manufacturing and characterization and other processes. Now, we have looked at a 2-dimensional case so far, remember. So, we had no stresses acting in the third direction. How would the Mohr circle look like when you have the third circle or the third direction also having some stresses? That is not very difficult to judge or difficult to say from here actually. It is just a simplified or extended version of this. If you have a 3-dimensional stress condition, it is not represented by a sphere, but still by circle, but now instead of one circle you will have 3 circles. So, this is still represents the x axis still represents normal stresses, y axis still represents your shear stresses, and over here this will represent your sigma 1, sigma 2, sigma 3, and if you look at this you will be able to get for a particular orientation what is the value of sigma x, sigma y, sigma x y, sigma y x and so on, and this will represent the maximum shear stress that exists. So, now you have 3 principal stresses being defined, sigma 1, sigma 2 and sigma 3 when you draw it like this. So, in this particular case we have 3 dimensions stresses in even outside the plane. So, in that case this is how you will draw, and again you can get the values of principal stresses using this. We will not get into this again, like I said, you can find out once you have the proper understanding of this. Extension to 3 dimension would be natural and it will be very easy. So, you can look about it in the books or even on like websites like academic websites like this. So, we will move on from here to our next part, which is strains. So, we have looked at Mohr circle for stresses so far. We will now try to understand a little bit about strains. Remember, stresses were a tensor quantity. What about strains? Actually, strains are also tensor quantity, and most of the things that we have described so far can again be very easily extended to our understanding for strain. All you need to understand first of all is that strain would be a tensor given like this. So, again we have some components some normal strains, and some others are shear strains. So, these are our shear strains. Again there is this similarity with stresses that we discussed earlier. Another thing that when we are talking about strains that you need to be aware of is that when we are talking about the shear strains, when I is not equal to j, what you measure is usually gamma, okay, and that gamma ij by 2 is what is taken in this tensor matrix, tensor table. So, epsilon ij, where I is not equal to j, is actually gamma ij by 2. That is one thing that you need to be aware of. And another thing is that you must be aware that strains are path dependent. Which implies that if you want to do some kind of transformation on these tensors, it's actually you have to be very careful. We will look at some of those constraints later on, but for the time being it is suffice to say that the strains must be very small for any such transformation, mathematical transformation. So, if you are transforming from one axis to another, or something or you are doing some kind of rotation, then in those cases you must check that the strains are sufficiently small, otherwise the transformation where the values that you may get may not really be a true representation of strains in that particular condition. So, other things that we talked about like Mohr circle. So, for strains also you can create Mohr circle. So, the strains Mohr circle and the stress Mohr circle, as long as the strain values that we are talking about are very small. So, just remember these values must be very small, and if we have those values as very small, then we can create circles just like that we created for sigma and just treat it as if it were similar kind of treatment. You can rotate it, you can get the values, all as long as the values of the strains are small enough. So, strain Mohr circle can also be created just as good, and they will be as good as the Mohr circle that we created for stresses. So, you can have principal strains, you can have normal strains and shear strains, you can get particular orientation in which you have only normal stresses which are called the principal stresses, sorry, the strains, principal strains, which will be when only you have normal strains, and you can in particular cases you can get only shear strains. For example, the condition we saw over here where you have some positive strains in the normal direction and the negative strains in the other direction. So, all those kind of manipulation and understanding can again be extended to strain Mohr circle. A few more things before we move on to something more, or not more important, but something where we will use these as the tool. Hydrostatic strain what is the hydrostatic strain? Hydrostatic components are the diagonal components and deviatoric components are the non-diagonal elements. So, hydrostatic strains are the one which cause dilation or volume change. And the deviatoric strains because we are dealing or we are going to deal with deformation. So, we need to understand which component actually causes volume change, and that is why we are listing it out here. So, there are two main components of strain, hydrostatic strains and deviatoric strains. So, hydrostatic strains are the ones which will cause dilation or volume change. On the other hand, deviatoric strains or kind of shear strains will cause distortion or shape change. That is for about strains. Now, let us look at hydrostatic stress. Again, the diagonal components are the hydrostatic stress. Hydrostatic stresses produce only elastic volume changes. Not the plastic. So, we have explicitly said only elastic volume changes, not plastic. But when we are doing deformation, which is the kind of deformation or the volume change that takes place, not the volume change, but the deformation is plastic in nature. So, the plastic deformation that takes place must be deviatoric in nature. So, deviatoric stress cause plastic deformation. If you remember your tensile stress strain curve, then we have the elastic region and the plastic region, and these two are separated by what is called the yield stress. So, in other words, we can say the yielding in a material. So, the corollary of these two is yielding. These are very important statements that you must remember if you are dealing with metal forming. Yielding is independent of hydrostatic stress. So, these, like I said, these are very important statements which will be converted into mathematical forms or equations which will help us get to our goal. And what is our goal? We will see. I mean, we know that, but we will put it in more in clear explicit words very soon. So, the corollary of this is first is that yielding is independent of hydrostatic stresses. So, you may have very large hydrostatic stresses, but it does not mean that the material will yield, it will deform plastically. Only when you have deviatoric stress components in the element in the material that it will actually start to deform. Now, having said that, let us try to understand what is yielding. We have so far always been talking about deformation, and deformation is plastic in nature, and that plastic deformation takes place once the material starts to yield. So, now let us look at yielding. We will start again with our simple understanding that we have already built over the years from our high school studies, high school knowledge and our undergraduate knowledge, which is of a uniaxial tensile stress. So, we have, so this is a uniaxial curve. On the y axis you have the strain, on the x axis you have the strain, and on the y axis you have stress. And how does this plot look like? So, this is our simple tensile stress strain curve. What are the different components of it? We know one of this. This is what we call as our proof stress at 0.2%. at the point 2 strain, if you make a parallel line along with the Young's modulus of the or the slope of the stress strain curve in the elastic region, then it will start to intersect the curve at some point, and it is this point which is defined as yield stress or Y. So, it is a stress value at which the material starts to deform, and again let me, to for the sake of completion, let me draw a simple. So, this is a simple dog bone which you may be stretching in tensile condition. So, you are put it in a UTM, which is a universal tensile machine, and you are stretching on the using two cross heads onto these side, and this is the region which gauge length which undergoes deformation, and it is in this region that we are looking at all the stress and the strain part. Over here up to this point we say this is elastic, and beyond this the material is plastic. Now, when we are interested in deformation, we are always interested in the plastic zone of the material, not in the elastic zone. So, this is the region that we are interested in beyond this Y point, and that is why we are interested to know where does this yielding take place. Now, here in a uniaxial tensile test, if this is your sigma naught, this is also equal to your sigma 1. So, and other sigma 2 and sigma 3 are 0, sigma xy and sigma yx also does not exist. Therefore, it is very easy. We are just concerned about one particular stress value, which is sigma 1 or sigma yy it can be. So, we know that all other stresses are 0, and therefore, we can just look at this value. Okay, this value reaches y. Okay, this material is yielding. But do you remember when we are talking about more complex shapes, the stress conditions are different. There is not only one stress anymore, it is not only sigma yy or sigma xx, there may be as many as 7 different components, and therefore, there we need to find out what particular condition in what will be the values of those at which it will start to yield or it will start to deform. Okay, so, but before that let us look at some more of these parameters. This is the point which is called UTS or the ultimate tensile strength. So, this is again a stress value, and the strain related to this is also unique, not unique, but is also very special, or it has some significance. It only up to this region you get uniform elongation. So, if you were stretching it, this is the gauge length onto which you have applied the stress. So, this whole region is getting elongated uniformly. At each and every point the strain is constant or similar. However, beyond this point what happens? Something happens, and it is called necking. So, in some region you may develop something like this. So, you see now this is a neck or a thinner region, and in this thinner region most of the stress is now concentrated, and so most of the deformation will be concentrated in this region, and therefore, it's the elongation that you see beyond this is no more uniform, it is concentrated in only this part, and therefore, this is non-uniform elongation. Beyond this are called necking, and at the end point you get what is called fracture. So, this is the stress strain plot that we have been seeing from long time, from as early as high school, and this is what it represents. And at this point, since now we have already talked about engineering stress versus true stress, engineering strain versus true strain, what do you think does this one represent? Is it engineering stress strain or true stress strain? By looking at these E and S, you may have guessed that it is actually engineering stress strain. engineering stress, engineering strain. But there is still another way to find out whether what we are dealing with or the plot that we have drawn is actually for engineering stress, engineering strain, or is it true stress and true strain, and that is to look until the point of fracture. Now, if this curve at all comes back, why is this coming back? Because over here you remember in engineering strain we start with just the original area as the base area, but in the true strain we took look at the instantaneous area. So, in the instantaneous area, if you are looking at the stress should always increase because the stress is F by A. So, the instantaneous area is getting reduced. So, the force by area term, which is the stress at that particular region, will keep on increasing. But on the other hand, when we are talking about engineering stress, our A remains constant. So, although the force may be limited, the load may be limited to this region in a very small region, but we are still looking at a very large area. So, because of that the plot seems to be curving down, when in reality the stress, the required load is still increasing, and that is how you can look at the plot. If it is coming back down, you can say it has to be engineering stress strain, and a true stress strain plot, it will not come down, it will keep on increasing, because as long as you are applying load, the stress must be increasing, and in fact there is something called as work hardening we will look at. So, because of the work hardening, the stress has to keep on increasing, and therefore the plot should keep on going up and should not come down. Anyhow, so coming back, so this is our stress strain plot, or to be precise, engineering stress, engineering strain plot for a uniaxial tensile condition. And as we saw that here we were concerned with only one parameter. As soon as sigma yy or sigma xx, whatever it is, reaches y, value y, so start with 0 and up to some point it will reach y. As soon as it reaches y, what happens? It starts to yield, or the material can deform, is actually plastically deforming. However, as I mentioned it couple of times before now, that when you have more than one stress components, more than one stresses acting on each and every element, then you have to find out not only about sigma yy, you have to also say what should be sigma xx, what should be sigma xy, what should be sigma yx, all these. So, should it be independently defined? So, let me rewrite it over here. Sigma, what should be sigma xy, what should be sigma yx, what should be the value of these components if we want to find out if the material will deform or not. And that is why we need a way to define the yielding of the material, and this is why it is where we need what is called as yield criterion. One thing that in a elastic region, the form of the equation of in the elastic deformation is very straightforward, and in fact it is very exact. It is given by Hooke's law. So, you know that y is equal to E times epsilon. E is your Young's modulus and y is your stress. So, or you can say sigma is equal to epsilon times E. So, over the elastic region the equation is exact. In the plastic region, even for a uniaxial condition, the form of the equation is not exact. We do not know, we have empirical knowledge about that, and some of the equations that are used are something like power law. So, it is given by sigma equal to k epsilon to the power n. This is defining how much stress you need for a given deformation where k is some constant. So, these are some of the forms of the equation, and again this is only related to, so far what we are talking about is uniaxial. In again multi-axial condition, again you will have to think about how to define this plastic deformation. should we define only for one sigma, which can be sigma yy or sigma xy or sigma xy and sigma xx and so on, again up to 7 or even in a simple 2-dimensional case up to 4 values. So, all those things you have to be able to define and look at when we are talking about yielding and the plastic deformation. So, we will come back to this in the next lecture, and we will start with discussing what is called as the yield criterion. For a material which is subjected to multi-axial stress, how do we define at what particular condition it will start to deform, and that is what is called the yield criterion. There are mainly two, Tresca criterion and von Mises criterion. So, we will look at these two in somewhat detail in next class.